Okay. 2 o'clock. All right. So next up, we're going to talk about classes and extensions, okay? Before we talk about classes and extensions, though, we also have to talk about what a reference type is. And my focus is not on the thing, so my clicker doesn't work. Once again, there we go. Okay. So, reference types. Reference types are the other kind of type other than value types. Value types do what we called assignment by copy. Reference types do what's called assignment by reference. And I know that that's a circular definition, so we'll actually talk about what that means so you understand it. So, when you assign by reference, you get something very different than when you assign by value. When you assign by value, you create a copy. That means it duplicates all of your stored properties, all of your data. When you assign by reference, when your type that you are using is a reference type, and you assign that or pass it to a function, which is essentially the same thing, you're passing a pointer to the same point in memory as the initial variable or constant that you are assigning from. Okay? So you're passing the same piece of data, right? You're not copying it, it's the same. What this means is if you make a change to one of these variables that is pointing to the same piece of data, then from that other piece of data, you can access that change, and you will see that change. And this can cause you all sorts of problems. It is one of the most powerful and one of the most difficult things with object-oriented programming, okay? It's why there is a very strong movement now to try and make as many types as you can value types and structs, because you don't have to worry about this issue. Because this issue causes a lot of problems when you're dealing with concurrency. If you have multiple threads all making changes to the same piece of memory, your program will crash, right? And it's very hard to not do that when you're dealing with reference types, because that's just what they do, right? But everyone's gotten used to reference types, so we have all sorts of ways to get around that, and special kinds of types like called actors that we'll talk about when we go into concurrency. They kind of allow you to use reference types safely with concurrency without having to like make everything immutable and transactional and purely functional, right? But the key thing to know here is that if we create a constant decoder 1 that has a instance of the JSON decoder reference type, right, which is one that you get from the foundation library that Apple provides. I guess I never talked about how you get libraries. You use this import and then the name of the library. That's pretty standard in a lot of languages. The exact syntax is different, of course, but in Swift, you just call it by the library name, and then you just call import in front, and then you have access to all of the functions and types and everything that were defined in that. So here we assign to the decoder 1 constant a instance of JSON decoder that we create by calling the JSON decoder's initializer, by calling the JSON decoder type by just using its type identifier, and then 2 parentheses. Its initializer doesn't require any parameters, which is nice. It means we don't have to pass anything in, so we just get it kind of for free, right? So we have a decoder 1. Now then we take that constant, we also assign it to the decoder 2 constant, right? So now we have 2 different constants, right, that have a reference to the same piece of memory, okay? So if we print decoder 2.allows JSON5, which is a property, a stored property on JSON decoder that defaults to the value of false, right, which is why we don't have to pass it in to the initializer, okay, then it will show false, right? But then if we change it to true using the decoder 1 constant, right, because we're changing the same underlying data in memory, when we call the exact same line of code just later, it prints true. And that's because the data has changed. The underlying data has changed, even though we're using different variables and constants to access it, okay? This is really important. So if anyone has questions about this, I am happy to answer them. If you've seen this before and you know exactly what this is, awesome, great, perfect. So yeah. Okay, moving on. So Let's talk about classes. Classes are reference types, okay? They are types that you can define that are a reference type. So here's a class, okay? We have also defined a small, cute little struct up top. We did it all in one line. It's adorable. It is a position. It is an x and a y that are an int, okay? Let's pretend that it's the coordinates on a chessboard, for example, okay? So here we've defined a class. You define a class in the exact same way as you define a struct, except you use the class keyword, okay? You create properties for that class in the exact same way. Stored properties, computed properties, all of that, exact same way, right? You create initializers, custom initializers the same way, okay? The main difference between classes and structs when it comes to initializers is that classes do not have the concept of a default initializer. They do not create a default initializer for you. We are able to make this cute little struct position without having to define an initializer because structs get one for free, right? Classes don't, okay? So we have to provide one even if we don't want to, even if we'd rather not, right? The only way you can avoid providing an initializer for a class is if all of your stored properties have a default value assigned. If that's the case, if your properties are all stored and have a default value, such as var alive equals true, right? Or you have all computed properties, or your class only has methods on it, right? Then you don't need an initializer, okay? Basically, Swift looks and sees, hey, could any of your non-optional stored pieces of data be nil right now? If so, you need an initializer, and you need to make it so that that's not the case, right? However, that's a pretty... It's not rare, but you just won't run into that much. Typically, you're going to have stored properties. And you want to have some sort of code that runs when you first create an instance of your class. So, our class has a stored property position, right? Position is a struct type. It's a value type, right? It's light, it's lean, it's got x, y, it has 2 ints in it, that's it, right? It's very small. It's almost like an int tuple, if you will. But it's nicer because we can add more functionality to it later if we need to, right? A tuple, you couldn't do that, okay? So we can define multiple initializers for a class. This is true for structs as well. So you can create multiple different ways to define, to instantiate your class, to create an instance of your class in memory, right? And you can say, oh, I need these parameters in order to properly define my class, okay? Now, in this case, we have 2 initializers that allow us to make sure that the position stored property has a value in it. We don't have to worry about alive because that defaults to true, okay? So we could change alive if we wanted to. We could have an initializer that passes in alive and makes a modification. We could create an optional parameter on our initializers that passes in alive so that someone could potentially change alive if they wanted to, but you don't have to do that. You do have to make sure that self.position is set, right? Oh, and actually, great point. You can see that I copy and pasted some code because I wrote self.position in this second initializer when it's strictly not required, okay? And it is best practice to not write self.dot if you don't need to, as we talked about before. So that's what I get for copy pasting code, and that's what you'll get for copy pasting code. So try and avoid it. Do as I say, not as I do. I know you won't, but don't worry about it. So we have our initializer that gets a position, and then we just set self.position to that. Cool. We're copying the value like a couple times here, right? But that's okay because it's just 2 ints. They're really small. It doesn't matter, right? We also have another initializer that just passes in 2 ints because we know that's all we need to make sure that position is properly set, right? And so we can have any number of initializers, right? You can also do a bunch of stuff called required and default and all these other keywords that you can add to initializers. Those more have to do with subclassing, which we will be talking about soon this lecture, but don't worry too much about it. That's something that it's covered in the reading as well, but you probably won't need it. It's kind of extra. I find I never use it, or when I use it, I'm using it for a very specific thing, and I have to look up how it works every time. So you don't need to know it. Okay, cool. What I'm saying is it won't be on the quiz. That's that. So our class also has a method on it, isValid, and that method always returns false just because I was running out of space on the slide deck. So, but this is called in exactly the same way as you would call a method on a struct, right? So we could write piece.isValid, pass it a position, and then it would return the value false to us, and we would make a decision based on that, presumably. You instantiate, you call it the same way as you do a struct, right? You call the initializer, whichever one you choose, right? When you're typing chess piece, you'll get a nice little pop-up of auto-completion. It'll show you all the possible initializers you could use. You'll find that Swift Foundation, like Swift Library, the ones that Apple write, like a lot of their class and struct types have like 20 initializers. They'll take all sorts of things. So don't worry too much about that. Just look for the right one that you're looking for. With that matches the data that you have for whatever you're trying to create. Cool. Okay. Any questions about defining classes and how they are different from defining structs, in that they really aren't, except for the fact that they don't have a default initializer? Cool. So next up, we have subclassing and inheritance. So I have this one slide for a topic that deserves a course. Subclassing is a way to shortcut get the same functionality in one class as you have already created in another. Okay? So if you want to, say, reuse a bunch of code in a class that you have defined. You've written a class like, say, chess piece, and you're finding that you're going to be writing another class, that's like king piece, right? It's the king, right? And you want a lot of the same stuff. Well, I guess you wouldn't do it like that. Let's say you write a king piece, and it has all the stuff that we wrote into chess piece. Then you go to write a queen piece, right? And you're finding that a lot of that code is the same. It's almost all the same, right? You might think to yourself, oh man, this is weird. Should I create some functions that I could access, right? Like outside that I can have these call and then, but those would have to be like global functions, which means everyone has access to them. It's no good, right? So how do you share code between these two different classes, right? How do you make sure you're not writing the same thing twice? And when you make a change to one, it applies to both, right? The way you do that is with inheritance, okay? We're going to talk about one kind of inheritance today, and then in class 4, I'm going to talk about the most important kind of inheritance, okay? But today we're talking about one kind, which is subclassing, okay? So when you use this fun :space syntax after a class definition, you are saying, hey, whatever type comes next is another class that I'm going to be a subclass of, okay? That's going to be my superclass. I'm going to inherit all of its stored properties and functionality, okay? I'm going to behave in exactly the same way as it, except for whatever I make different, all right? So here, if for example, we didn't have this method, right, isValid, if we didn't have this change here, right, then king would act exactly the same as chess piece, okay? It has the same stored properties, it has the same method, isValid, right? And it would just behave in exactly the same way. Swift would cause you some issues if you ever tried to intermix those types, right? Because they are not the same type. However, there is a concept called polymorphism, which I think Swift, the documentation prefers a different, newer term. Polymorphism is what I was taught in the noughts, so bear with me, I'm old. Basically, the idea that a king instance can be used anywhere in code where you want a chess piece instance, okay? Because it is a subclass. That guarantees that at least has all of the same data and functionality at minimum that a chess piece has, okay? That's the main thing about subclassing is your subclass cannot remove functionality from your superclass. It can only add to it, okay, or change it, okay? So it can add or change, but it can't remove, which means anywhere we want to use a chess piece in our code, if we, say, wanted to pass a chess piece to a function or something like that, our function parameter says its type, for the parameter is chess piece, we could pass a king to it and it would work okay, all right? Don't exactly quote me on that. I know Swift has a few things where it tries to be a little bit more clever with that to make sure that, but I think that has more to do with protocols, which we're going to cover in class 4. I'm pretty sure when it comes to subclassing, polymorphism still applies. So, another thing to note, you can only ever subclass from one class, from one superclass, okay? You cannot say, oh, we're going to have a chess piece superclass and a mini statue superclass, right? And the mini statue has all like the physical properties of like the actual piece, and the chess piece has all the logical properties for like, moving it around the board or something like that, right? That's not something you can do with direct class inheritance. You can do something like that using protocols, which is why they're very important, but we're not going to talk about that today. Today, it's just good to know that one class can have many subclasses, okay? But every subclass can only have one superclass, and that's what you call your parent, or whatever class you're inheriting from, okay? For a long time, people also called this extending a class. We don't use that terminology in Swift because extensions are a completely different thing, and you will be learning that this lecture as well. So if you see people talking about extending classes, they might be talking about subclassing, and they might be talking about Swift extensions. It depends on the context. Okay, cool. So that is what subclassing is. So that's the concept of subclassing. Does anyone have questions about that before we get into whatever the heck is happening with this is valid function? Cool. So with this is valid function, we are doing what's called overriding functionality, okay? So we've used the override keyword, and that is our way of telling Swift, hey, so the king class is going to behave exactly the same as the chess piece class, exactly the same, but whenever someone calls the isValid method on an instance that is a king, instead of calling chess pieces method definition, right, and using the code there, we want you to call this one instead, right? It's gonna still interact with the exact same stored properties, right? You can still access any other functions that you didn't override, right? So if there was like another method that was like, I don't know, hair color, whatever, right? Like get hair color and it returns a string or something like that, right? You would be able to call that from within this method, okay? You would just do self dot hair color. And actually, I don't think you would even need to do self dot, but you might because it's calling a superclass. I don't remember the exact syntax, but the compiler will help you. So you can use and call any stored properties, computed properties, methods, anything that was defined in chess piece, you can call in any overridden method in king, okay? So here, in our code, we define an instance of king. It has x is 3, y is 2, okay? And we then call king.isValid, okay? King.isValid target, and then we pass it a position, right? Now, okay. There is a syntax error here. The compiler would have caught it if I wasn't trying to do clever animation things and copying code over without it being compiler ready. Your function definition when you're overriding does have to be exactly the same, including your argument labels and your parameter names, okay? Here isValid has move2 as its argument label and parameter name, which, by the way, are terrible argument labels and parameter names, which is why I changed it. But then I forgot to update that line on the slide. So pretend that this isValid move2 position is actually isValid target position in chess piece. So down here, we're back to this. King.isValid target position. We're pretending that that's what this is up here in chess piece. So if we had not overridden the function, when we do that call, then it will use chess piece's functionality to perform the operation, because it doesn't, have another way to do it. But it does have access to everything chess piece did, okay? But because we've done an override of the method, instead it diverts it and says, oh, you know what? Actually, sorry, hold on. We're actually going to go over here to the king's is valid, okay? It's different behavior, different functionality, right? And this is something that you would, when you think about it, it makes a lot of sense, right? Determining if a target position is a valid position for a particular chess piece to move on a chessboard is going to behave differently for your different kinds of chess pieces, right? So you could imagine an entire system where you create a king, a queen, a rook, a knight, a pawn, etc., right? I think I said all of them except for bishop. And then here, we just do some calculation to say, hey, anything that's adjacent to me is valid. Cool. Which that's technically true. It's a valid move for a king unless it's blocked, but that's a different discussion. So, any questions about how subclassing and inheritance work? I'm laughing because it's one slide, and it should be like a class, like a whole 14 classes class. So, any questions? Cool. It's very important how this works. All the things that we talked about. Okay. So continuing with our subclassing and inheritance, we can take a look at how this interacts with having multiple different instances of king, right? So it's just important to note take this off. Wrong pipe. Ooh. Excuse me. Oh, I hate that. Okay, we're clear. Whew, made sure I didn't cough into the mic too much. That'd be awful. So here, it's just important to note that we are creating different instances here. So here we've created a king, a white king, and a king, a black king. Your standard chess colors, right? We have set the white king.alive to false. If you know anything about chess, you know that would never really happen. King never gets taken, it gets put into checkmate. That's how you win. Excuse me. But for demonstration purposes, that's what we're doing here. You can pretend it's a queen if you want. So here, when we call white king.alive, we are getting the false value because that's what we set to false. When we call black king.alive, we're getting the true value because by default, alive is set to true in the chess piece class, right? We're not even doing that in king. That's just a chess piece thing. The piece starts alive. It starts with the alive property set to true. Okay. So you can also do something called downcasting, and you can also check type. So downcasting is that thing that I was kind of talking about where one type can kind of act as another type. Here, you can use the keyword as with no question mark, where we do king as chess piece, okay? And we set that to the constant king piece, okay? Moving forward, the king piece constant has a type of chess piece, even though the thing that we were actually that we actually stored, right, was a king, okay? So it's weird, okay? But so king piece is still pointing to the same piece of memory, all right, as king, okay? So our king constant here and king piece, they're pointing to the same piece of memory. However, whenever you interact with the king piece constant, you cannot access anything that was added by the king subclass, Okay, so if the king subclass added a new stored property, right, like crown shape or something like that, right? King piece, the constant, if you tried to do king piece dot crown shape, would fail. You'd get a compiler error because it's the wrong type. You've changed its type, but that's just the type of the variable or constant, right? It's the window through which you are looking at the memory, okay? So the memory is still backed by a king type, right? So you still have your stored property there, but you no longer have access to it because you have downcast it from king back to chess piece, okay? You've gone back to a chess piece. You've devolved, if you will. Your Charizard is now a Carmeleon. Yeah.
So why not just directly access to chess piece?
Sorry, say again?
Why not just directly access to the chess piece? Why we must use king as chess piece?
Why would we do this? Like, why ever, right? Because it's just removing functionality, right?
We cannot use or calling the new functions from the king.
Mm-hmm.
We will go back to the chess piece. So why not we just go directly to the chess piece?
Great question. So the question was, sorry, it just fell out of my brain. I knew it was a good question, and I just lost it. Say it again, sorry.
Yes, the king has new functions,
Mhm.
override new functions.
Yep,
The king piece cannot use or calling these new functions.
right.
So we need to use the king as chess piece
Mhm.
to call the functions from the chess piece, right?
Right,
So my question is, why not just go directly to the chess piece?
right. Why wouldn't we just have king be a chess piece,
Yeah.
right? Because sometimes you might want to instead use the king, right? You might also have a situation where you have a further down subclass, right, that you're working with in your code, right? But then what you're returning to other pieces of your code, right? All that extra functionality that you've added, right? New properties, new functions, overridden ones, right? You don't actually want any of your other code to access that, right? It's something that it's extra functionality that no one else needs, right? So it's just something that you're doing over here in this part of the code, right? Over here, you don't need to see that, right? So this code here is somewhat nonsensical. You'd never write it like this. It's just illustrative. It just shows what you could do. Does that make sense?
So it can directly calling the chess piece, but we write this to show we can do like this.
Yeah. This is just written so that you could, so showing that you can cast king as chess piece, that you can downcast king as chess piece, that you can turn it into a that you can assign a reference as chess piece. Does that make sense? Okay. Cool. Okay. Yeah, I saw a hand over here too. Yeah.
So for the king piece, if we look at the is valid, does it return false from
Mhm.
the chess piece, or does it do the calculation from the king class?
Right. So it would call, king piece would call the is valid from chess piece because it is of type chess piece, right? So one thing I didn't really talk about, and I should have, but I didn't. Okay, that's way too far back. I don't know what happened there. Here. So in our override function, there is a way for us to access the function that we have overridden, okay? There is a keyword called super that you can use to, I think it's super. It's either super or base. I think it's base in Java and super in Swift. I can't remember. It's one of the two. So you can call super.isValid target position and pass that in, and then that would call your parent function, right? That would call the inherited function, right? So you can do an override and add functionality, add code, and then still call the parent if you want. So it is still accessible. Basically, another way to think about this is rather than overriding, you're kind of creating a second new function that gets used by default when .isValid gets called on a king type instance, right? on a variable that has the type of king, by default it calls is valid. But within the king scope, it knows, oh, I'm a chess piece. I could call, anything else. I could call super dot, right? Any of my properties or anything that are overridden, right? And I can skip the override and get to the thing that I was kind of hiding, right? We're hiding it, but we're not removing it. It's still there. It's just kind of blocked. But there are ways to access it. So using super is one, downcasting to chess piece is another. Does that answer the question?
Yes.
Okay.
So downcasting is just, for some reason later on, we want chess piece, but with all of the information inside king, that's what we would use it for.
Within that king instance, yeah. So any of the data that we had stored in that particular instance of king that a chess piece also has access to, like is alive, right? Alive, right? But if we'd added a new property to king, like crown, we would not be able to access it if we had downcast it to chess piece. These questions are all excellent because you're basically asking, why would you do this, right? That's kind of what I'm hearing is this like, okay, yeah, sure, you can do that, but why? Why would you ever want to, right? And that's a great question that I did not answer in the slide because of time constraints. So I just wrote a simple little, kind of technically correct syntax that you would never actually write in real life because there's no reason to ever do that. And in fact, I think it gives a warning later on about this. So, yeah, does that, okay, cool. Any other questions about that before I move to the next piece, which is checking type? So anything else about downcasting and subclasses? Okay. And if I did not answer these questions effectively, do send me a message asynchronously. Sometimes when I'm up here talking, I miss the actual question that's being asked and answer something else. And if I do that to you 3 times in a row, I can understand that you might not want to ask again and get a wrong answer again. So feel free to message me or remain asynchronously, and we will be happy to answer for you. That way, and it'll probably be more accurate. Okay, so let's talk about checking type. Excuse me. Excuse me. Okay, so you can use the is keyword. Oh, I guess, sorry, I'm skipping something. We need to talk about as question mark. Okay, so as question mark is a way of saying, hey, I have my variable, my constant piece, right? It is a chess piece type. We also know that king inherits from chess piece, right? Which means that, like king piece, right? It could be a chess piece constant with a king backing it. So there could be a king underneath, but it's a chess piece to us. In our scope, when we're looking at it, it looks like a chess piece. That's all we have access to when we call it, right? If you want to try and kind of reverse Uno card it, right, and go from, say, king as chess piece, this would have actually made way more sense if this was king piece here. So I'm just going to say, pretend that's king piece. King piece as king, question mark. What this does is says, hey, can you, like, are you actually a king under there? Are you actually a king hiding beneath this chess piece? If you are, please return yourself as a king type, okay? So this expression evaluates to a king type if the backing type behind our chess piece constant is of the king type. If it is not, we return nil. Okay, which means that we have to safely unwrap it. And that's why the question mark is involved, because it is an optional, right? Because what gets returned could be nil or it could be a king, okay? So what we're getting is either a king or nil, right? And as a result, we need to do if let to safely unwrap our optional and have access to piece here, which, by the way, we're doing that thing I talked about before where we're overriding within this if-let scope, we're saying, hey, this piece here is now kind of replacing this piece, okay? So this is a new constant. It has the same name, but anytime we use it within this if-let block, inside of the brackets specifically, not outside the brackets, like here to the right side, the piece there is the previously defined one. But within the brackets, okay, we can, whenever we use piece, we're referring to the one that we just defined. We are overriding it, right, within our current space. So here, the type on piece, the if-let piece, is king, guaranteed. Once we're inside of that scope, that constant has type king. And you can do this print piece is king. Is a keyword that you can use to just check whatever the type of what you are looking at is. It'll say, oh, is this a king, right? And it will print out true. And in fact, that line will give you a compiler warning. It will say, hey, you're doing this check here and there's no reason to. Piece is always king. It's guaranteed. You can't get to this code if piece is not king, right? So yeah, but I didn't do the warning thing there because it's a warning, not an error. So, okay, so regarding that kind of conditional casting and the type checking, are there any questions about that? Okay, I know it's vaguely confusing, but I will hopefully be able to explain it a little better with better examples later on. Okay. Okay, so now we're talking about access control. When you create a type, be it a struct, an enum, or a class, sometimes you have some stuff that you need, some stored properties, some function, some piece of the type that you don't want to share with the rest of your code base, okay? We talked about kind of hiding things using downcasting, right, as we saw before. That is one way of doing it. However, the more common way is by using access control keywords, okay? So access control is a way to limit access to an entire type, to its properties, and to its methods. You can use it for making APIs. So access control is typically how you create libraries of code that other people will use. In order to safely construct your library, you're going to have to write a bunch of code that you don't want users of your library to access. And the way that you limit them is by using access control keywords. So this is primarily used when you're making libraries. The other thing that access control do is it kind of helps guide developers who are using your code. It teaches them and shows them, hey, this is what's important, right? By only allowing them to access what's important for them to access. And you can prevent developers from using your code in ways that you do not want them to, which they will try to do if you don't prevent them. So, in Swift, we have a few access control types. I'm only going to talk about the important ones. There are a couple more after this, but we're not going to look at them. The first is public. Public is basically fully accessible. You're saying, hey, anyone can see my type, anyone can see my variables, my properties, my methods. You use the public keyword, and then that property method can be called from anywhere by anyone. Okay? Internal is the next. Internal is the default access control level in Swift. If you do not provide a keyword, internal is the keyword that gets used. All right? So with internal access control, you are basically saying, okay, so anyone can use my type, anyone can call my methods, anyone can call my properties, anyone can access those. So if they have an instance of my type, they can do instance dot function or method, and then call it, right? But only people who are in the same Swift module as me, only code that exists in the same library as me can do that. Code outside of the library, code in a different module, right? And this is what you define when you make a Swift package manager library package, right? That's kind of you're defining a module, right? It's not technically true, but it's true enough for our purposes. Then any code that's like using that library won't be able to access anything marked as internal, which means if any code you write in your library you want to be accessible from outside of your library, because internal is the default, you have to mark it public, because otherwise you won't see anything. You'll import your library and then there will be nothing new in your autocomplete. You won't be able to use any of your types that you defined. So that's what internal is. That's the default. If you're writing a library, make sure to make at least some of your types public so that you can access them, or developers can access them when they use your library. Lastly is private. Private is hidden from any other type or scope outside of your type. Basically, only your type can access this. So essentially within the scope block defined by your class definition or your struct definition, this function or this method or property is fair game. You can call it. You can use it from other functions, from other methods in the type, from other initializers, whatever, right? Computed properties, etc. However, you cannot call it from outside. So if you have your main file and you create your type, like an instance of your type, and your type has a isAlive property on it, right? That returns a Boolean, but you've marked it as private. If you try to use instance.isAlive, it won't work. There will be no autocomplete. You'll get a compiler error if you try and compile that. It is hidden from you. Only code that is within that type can access it. This also hides code from subclasses. So when you write your subclass, if there is a private property, you can't access it inside the code block of your subclass. So, yeah. A lot of other languages have a concept called protected, which is basically private, but subclasses can access it. Swift has decided, no thanks, we don't want that. It's dangerous and we don't like it. They've made a choice, capital C. Is it right? Is it wrong? I don't know. Okay, let's take a quick look at access control. So here we've defined a class called chessboard. We have added the public keyword in front of it. That means that outside of our module, we can see the type chessboard. Cool. Unfortunately, we have defined our property, squares, as private. What that means is that any code that's written outside of this class block cannot access squares, okay? So all the code in the initializer works just fine. We can set squares, we can do this other stuff, right? But we cannot actually access it from outside. If this code was written in any function, any other class, in your main, whatever, when you do board.squares, you get a compiler error. It's inaccessible due to private protection level, right? Because we've made it private, right? There is another problem with this code, right? Which is that, yes, our chessboard class is public, which means we could access it from outside of our module or library. However, because everything else is either private or internal, because the initializer is internal by default, we can see that type, but we wouldn't be able to initialize an instance of it. So chessboard pieces, brackets, if that was outside of the module, if it was, some other piece of code that was using this as a library, then we'd get that same error. We'd get chessboard initializer is inaccessible due to internal protection level, right? So when you're writing libraries, you just have to be very careful about what you allow to be internal by default, what you set to public, and what you set to private. Private things are things that you don't want anyone else to see. It's just for you. Pretend it's your little scratch board, right? If you're ever writing like a paper or something, you'll probably have your paper, and then you'll probably have a completely separate file or piece of paper that you're using for notes, right? Things that you don't want to be in the final product, right? But that are helpful for you as you write the final product. That's kind of what private is for. Okay, any questions about access control? Cool. All right, extensions. So we're going to talk about Swift extensions. I'm going to drink water, and this time I'm going to try to not choke on it. We will see what happens. Cool, we did it. I'm also going way over time, but that's because I didn't give myself enough time for these topics, which are very complicated. Okay, extensions. So In Swift, extensions are not the same thing as when people talk about extensions in other classes and other languages. They talk about extending a class, that's just making a subclass. That's what they mean, typically. In Swift, an extension is different. It is a way to add functionality to existing types. And I can hear your thoughts saying, well, isn't that what a subclass is, right? It just adds or modifies functionality. And that or modifies is really key, because an extension can't modify existing functionality. It can only add, okay? The other thing, though, is that you can add, with extensions, you can add functionality to Apple-defined types. So if you are finding that you are constantly doing the same thing to strings, right? That strings are just, in your code, the way you use strings, you're just constantly finding that you're going to have to, you have to pull it, you have to do the thing where you, take the first half of the string, take the second half, and swap them. I don't know why, you're just doing it a lot, right? You could write a global function to do this for you. But global functions are kind of, they're risky, they're not clean, they're hard to find, right? They're not discoverable. It's preferred to avoid them, right? You could write a class that has this functionality with a static function, right? So it's my string dot call my static function that swaps my strings front and back, right? So you could do that. Or you could use an extension on string. So you could modify Apple's string type and add a new function to it. So that you could then just you should have your string, either a literal or a variable or constant that's a string type, and then you could just call that dot the function you define, right? And it works. So some of the things that you are allowed to add with extensions. You're allowed to add computed properties. This list is going to look very familiar to you when we talk about the things. It looks very familiar to you in terms of things that are on both classes and structs. Not everything, but a lot of it, okay? So you can add with extensions computed properties. You can add initializers. You can add methods. You can add subscripts. And you can add nested types. Note, you cannot add stored properties. Stored properties are a no-no. You're not allowed to add them with extensions, okay? Cool. What that means is basically, you'll note what that means is that while you can add functionality in classes, you can add functionality, right? You cannot add data, all right? Which means you're not really modifying the memory signature of any particular instance, right, of string, right? You're not changing how much space it would take, okay? Okay, cool. So let's take a look. So here we're going to do an extension. Let's say for our chess board that we have this thing where we really want to be able to just say, man, I wish I could just use the letter A and have it just be the number 1 because that's the correct coordinate for that axis on a chessboard, right? And same thing with B and C and so on and so forth, right? A good way to do this is with a dictionary, right? Which is what we've defined here. So the dictionary is just a lookup, right? Where you say, oh, okay, cool. So, A is 1. So if we pass A into this dictionary, then we get 1 back. If we pass B in, then we get 2 back, so on and so forth, right? Excuse me. So this is a static property, okay, that we've added. Now, and again, that list was not fully complete of the things that you can add with extensions, because here we have added, this is a stored property, right? And I was like, oh, you can't add stored properties, right? But because it's a static stored property, it's not going into the instance memory, it's going into that one kind of global place where, the memory for all character functions and static things are defined, right? Where all the code and everything, where it calls that, right? So that is where this gets stored, and as a result, you can use static stored properties on extensions. Cool. So what this means is basically anytime you have a character type, which in Swift, a string with only one character in it also can be used as a character type, then you can call .lettermap on it and pass it a character. Sorry, Yeah. You can also do it just using character.lettermap. You don't need to have an instance of character, which would be a much more intelligent way of doing it. There's a bunch of other things you can do with extensions there, but we're going to look at the next piece. There's many ways to do this concept, and this is not what I would call the best one, but it's illustrative of static stored properties. So now, let's say we want to be able to have a situation where we pass a string like A1 or B1 or C2 or so on and so forth, right? The way that you typically talk about positions in chess, right? Okay, great, cool. And we'd like to be able to get a position back, right? You remember our position struct, right? It has an int, it has an x int, and a y int has stored properties, right? So here we've written a function on string that says, cool, okay, so self is the string that you're calling this on, right? So self.first. When you call dot first on a string, it gets the first character in the string, if it exists, right? That's why we have to put it in an if-let block, because self.first returns an optional, because it might not exist. A string could be empty. It could be an empty string, and there could be no first character. But if there is one, we get it, and we put it into the letter constant. Okay. So then here we do character.lettermap letter. All right. So whenever you are calling into a dictionary and you are simply passing it a key, like so, you're passing the dictionary a key, what you get back is optional. Okay. It's not guaranteed to exist in the dictionary. There's no way for the compiler to know if it exists in the dictionary because letter is not, a constant or anything. So what gets returned by that subscript is optional. So we have to unwrap it, which is why we also have this as a part of our if-let definition. One thing we didn't really talk about when we went over if-let, if you want to do multiple if-let unwraps, rather than having to do if-let and then the brackets and scope, and then another if-let, brackets and scope, if-let, brackets and scope, inside, you can use commas to just separate them from each other. And Swift knows that that's basically the same thing as nested if-lets. It prevents you from having like a million indentations when you need to unwrap a bunch of things. But these commas are essentially like double ampersand in terms of Boolean. So we'll only enter this if block if every single unwrap occurs correctly, and letter X and Y are all non-optional, okay? So then here we do self.last. Self.last is optional, which means if we want to call any further property or method on it, such as whole number value, we have to optionally chain it, right? So we put a question mark and then a dot, and then that says, okay, cool. If this exists, then call this property whole number value, and if it doesn't exist, just return nil. That's what optional chaining does. So that's what we're doing here. Self.last, question mark, dot, whole number value. And whole number value is a computed property on characters that can turn a single number character into an integer. But that is also optional because it can fail. If you pass it A, it will fail and say nil, right? So we have two ways this can come back nil, but we only have to unwrap it once. So we get let y equals, right? Then once we're inside here, we can return position X, Y. Okay. Of note, we're using letter, which we unwrapped earlier in the if-let, right? We use letter here in the letter map, and we can do that because we know by this point in the if-let, it is safe and unwrapped and no longer optional. Cool. So now we have this function chess position on string. Never mind. Okay. So when we have this function on string, we can call it on any string instance. Okay. So anytime we have a string, we can just call chess position. But I think I have an example further on, so I'll just go through and see what I was trying to think about before. I'm not sure why I did all these switches. They were basically in the same position, but whatever. So I think we're just shrinking things, right? I'm asking my past self. Yes, we are. Okay, cool. So here we have our final situation, which is we are calling on we have a string literal where we put F3 inside, and then we can call .chessPosition, this function that we've added to string. So now the string type that Swift defines, that Apple has defined, we have added something to it. We can now call our custom functionality on that string, on any string in our code, and we can get from it returned, whatever, right? And in this case, F3 returns position x6, y3. Cool. Okay, any questions about extensions so far? Awesome. Okay, so I have a 10-minute break here. However, it's 5 till 3. I can try and talk about generics today, but I think that that's probably a fool's errand. I just talked for a very long time about classes and extensions, and your brains are probably kind of full of that. So I can talk about generics in a quick high-level way, but I will do an in-depth lecture piece on generics next class, which actually pairs very well with protocols. Generics and protocols work very well together. So, but I will do a quick overview of generics using a playground, just to kind of give you a feel, but it won't be on the quiz. So the quiz is only going to be on enums, structs, and classes. Cool. Any questions about that? Awesome. Okay, so let's go ahead and close this. And we will open up a playground. Excuse me. Thank you. Here we go. Okay. Where'd it go? Here we go. All right. So, generics are a way for us to basically have as a piece of a class or a struct an unknown type, a type of indeterminate origin, something that we don't know what it will be until it gets used, until our type gets used. You see this in play all the time. So far, we've seen it in play constantly. Arrays, dictionaries, all collections, right, use generics. An array could be an array of ints, or it could be an array of strings, or it could be an array of doubles. We don't know. It could be an array of literally anything, as long as it's all the same, right? Same thing with dictionaries. It could have string keys and int values, or vice versa, right? However you want to do it. And the way that you do that, the way that you can write types that have that same concept of flexibility of, oh, I could be, I could have like these things, right, is with generics, okay? So one of the ways I was going to illustrate this was using trees, because the assignment I was planning on giving you all was a advanced form of the calculator that the previous assignment was, which actually properly handles parentheses and order of operations and multiple stuff. You do that using something called an expression tree. I don't have time to get into trees right now, and not into generics enough for that assignment to make sense. It will be popping in the module soon. Please ignore it. I will be replacing it with something different. Apologies. So I will do that tonight, and I will send out an announcement on Slack and in the Canvas once it's changed. But for now, let's go ahead and take a quick look at, let's say we wanted to make a stack. A stack is a data structure that has a first in, last out mentality. So basically, think of it like literally a stack of things, okay? So rather than, an array is kind of a line of things where it's like, oh, something goes into here and here and here in slots, right? A stack is where you just say, all right, just shove it on. Okay, here's the next one, just shove it on. Just, make a pancake, build a sandwich, right? So first you do the bread, then the salami, then the lettuce, then the tomato, right? And then if you ever want to take things out of your stack, you pop, right? So you push and you pop, okay? So when you pop, you just take something off the top. So when you're disassembling a sandwich, right, you take off the top piece of bread first. You wouldn't ever try and hold it up and slip the bottom piece of bread out. That's psychotic, right? Of course, you also probably wouldn't ever disassemble a sandwich, but you would if you wanted to maybe add a condiment at a certain layer, right? If you're like, oh, they didn't put ketchup. Let me, get my ketchup. I don't know, salami, lettuce, tomato, and ketchup? What a weird Sandwich. Anyway, so a stack is basically, that's the data structure, okay? So there are a lot of different ways to implement stacks, okay? And I don't remember all of them off the top of my head, but let's just take a look at what we would do to kind of set that up at a high level. So to start with, this is a collection. It's something that stores other data types, right? Or other types. In Swift, collections are structs. They are value types, okay? So we have our arrays, we have our dictionaries, all those things. They're value types. We're going to follow Swift's lead. We're going to make our stack a struct. We're going to make it a value type, okay? Of note, if a value type holds references to reference type, the reference gets copied, not the memory, okay? So structs pass by copy, right? But if it has as one of its like properties a reference type, right? It's not going to copy that reference type like the data in there as well. It just copies the reference to it. So it's still modifying that same thing. Try to avoid that if you can. It kind of breaks a lot of stuff. Okay, so let's go ahead and look at this. So we're going to create a struct. We're just going to call this stack, okay? We're just going to do this stack. We're going to do it by having an array that we just mutate, okay? So we're just wrapping around this. So we're going to create our array here. This will be private. We don't want anyone to have access to this because we're just doing this ourselves, okay? And now we need to have a type in here, okay? So we could say, oh, this is a stack of ints, right? And then we'll just call this like int stack, right? And then, you know, moving forward, we can be like, oh, okay, cool. Now we need a stack for strings. Okay, we'll make a string stack, right? Okay, you see where this is going, right? It just keeps doing the same thing. We could do this for every single type that exists, and there's an infinite amount of types because you can make your own types, okay? So say type 5 times fast. Type. So how do we handle this? You use something called generics. So this is the basic syntax for a generic. You've seen this before. I talked a little bit about it when I was talking about collection types. I showed this is kind of what gets used for the basic initializer, but luckily Swift lets you get away with not having to refer to this because it's a little cumbersome when you're initializing things, right? But here we have this, and I shouldn't say int here. So inside of these, basically you create a kind of placeholder type, sort of a variable for a type, if you will, okay? Something that could be any type, all right? So a lot of times people use T, which is like T for type, right? That's kind of silly. Swift tends to use element for collections, so we'll follow their lead, okay? So basically anywhere we see the word element used within our struct, we are going to be referring to whatever type is assigned to that particular generic instance, all right? So here we have element, okay? And you get autocomplete here, and it has that T, right? Because this is a generic type, right? Okay, so it's just saying, oh, cool, element, right? Got it. So now we have this private thing. We also have a default initializer, okay? So we know that right now, if we made a stack, right, like this, it's going to ask us for an array, okay? And it names the argument and it names the parameter after what our things are, right? So it does this, okay? Now, you could, if you wanted, to prevent the default initializer from asking for something, you could do this, right? However, you get an error here, right? And the error is that the generic, whatever it is, cannot be inferred, okay? That's basically saying you weren't explicit about what it could be, and we also couldn't guess what it could be, okay? Swift is very, very good at inferring generic types, all right? That's what it does all the time. That's the whole thing that we do whenever we're like doing, like let's say here we have an array and we set it to this, right? Because it knows that these are int literals, because it knows that the type of the elements inside of that array are ints, it says, oh, okay, cool. So this array has for its element type int, right? And that's the case just for this particular variable. It's not that case for all array variables, right? All variables that could be of array type. Just for this particular instance, that's the type we're using. So here we have this error, right? So you could say here, do this, okay? This is the default kind of way of doing it. This is not default, sorry, but this is like kind of the official way of doing it. This is how you'll see it in other languages like Java and stuff. They typically tend to do it like this, okay? Where it says, oh, cool, this is how we do it, right? But because Swift is really smart and you've told it that this particular, variable, this particular property has the same type as our generic, right? It has our generic type. And the default initializer is being set to have an input parameter that has the same type as that so that it can be assigned to it. Basically, what ends up happening is that you can just pass it an array of ints. And it's private, so it can't. Is that because, hold on. I forgot, structs do weird things with that. Like that. There we go. Wait, did I need that or did I just mistype? Hold on. Yeah, I did need that. Okay. So yeah, basically, structs can kind of be finicky with private, right? If it's private, it will create an initializer for that, right? But it will be a private initializer, right? So by default, it's doing this, right? So this is what's being created by default because all of our stored properties are private, right? It's just a struct being a struct. If you just override it and create a public one, then you're all good. But whatever it is, we don't want our backing type to be known, okay? We don't want anyone to be able to access it directly because we're a stack. And the only way you should ever be able to access things is by popping the last thing that was pushed on, okay? So here's our stack, and our stack is of type stack int, right? And it's telling us that here in the autocomplete. We can use it for that sort of thing. And I'll do a quick function where we do a push. And so we're going to push element, right? We're not going to return anything because you don't need to return anything. We're modifying it, right? And this is actually going to be mutating because we're changing the array, okay, right? So here we're just going to, the way we're going to do this is we're going to append, right? So we're going to do array.append element, right? And it's going to yell at us because we're trying to mutate something that can't be mutated, right? So if we mark it as mutating, boop, then that error goes away. Dope, right? Cool. And then we can also, really quickly, actually, because stacks are super easy, you can do a pop, right? And this will return whatever the type is that we're using for that particular instance. And so we can do array dot, and we can do, where is it? Remove last, yeah. So you can do a return here. You can also just leave it like this, I believe, and it will be okay. So remove last basically does exactly what we want, which is it takes the very last thing at the end of the array, it removes it from the array, and then returns it, right? And then here we're just chaining that return, right? Remember, if we only have a single expression inside of a function and it evaluates to the same type as our return type, we don't actually need a return, okay? So we can just do this, all right? This is a stack. We have implemented a stack. So now you can do these things where, and here we'll start our stack empty rather than full, right? So, and in fact, you probably would want that actually. Stacks never really start with anything. So we'll just do that. And then we will also get rid of this like so. And now, of course, it doesn't know what element, right? So here we'll say int, right? Like that. So now we can push 1 and push 5 and push 10, right? And now we can print stack.pop, and we do this 3 times, and it will print while it compiles. Oh, it was too fast. 10, 5, and 1. So it does it in reverse order because it's a stack, popping everything off. Cool. So that's the basics of what a generic is and how they work, and we'll get into much more detail on them and the cool kinds of Swifty things you can do with generics and protocols and subclasses and stuff next class. Again, ignore the current assignment. I will take it down very quickly. Hopefully you won't see it ever unless you're looking at it right now, in which case I'm like, okay, I guess, fine. That's your prerogative. You're allowed. You can just look at my mistakes. It's okay. But yeah, I'll be changing that. It will be done tonight, and then I will send that out to everyone, like a notice once it's complete. Yes. The only other thing I wanted to ask, this is more of a question just for the class in general, and you don't have to answer now. You could answer just, asynchronously or otherwise. But one thing that I'm wondering about is the quiz review that I did today was for last week's quiz. The quizzes that I'm writing are by default auto-graded. They can be graded instantaneously, which means I can review the quiz literally as it's being done and finished. So I could do a review of the quiz right after you took it. Would that be more helpful than doing it a week later? So for the quiz review that we did today, it would have been, we would have reviewed today's quiz rather than last week's quiz. If you feel it would be helpful, let me know. If you feel it wouldn't be helpful, you can let me know that too. If you don't have an opinion or don't care, you can also tell me that. You could also not tell me any of those things if you want. So, yeah. Oh, and I should stop recording too, because this is admin